Let's start. Welcome again. And let me just recall what we did last time. So this is just the millionth time that I'm saying that I have a category set to the C opposite for some category C. And then I interpret C as the category of some good simple spaces with some sort of maps. And then I have also the big category, which is this guy, sets the opposite. Here, the objects are functors. I interpret any functor as some sort of generalized space, such that to any A, it assigns all in quotation maps from, say, A to some space for F, or let's say just F itself. And therefore, F somehow encodes locally in some sense. Locally means objects here. Some space, say generalized space, and some family of maps, right? Maps from simple spaces to it, right? There are two things that I'm encoding somehow, some sort of space and the maps. And then last time we had the thing that, okay, I don't like this situation simply because a geometry usually loves to work with local maps, not maps. And how to formalize locality, then we just went for this specific case, right? C is just the opens of a topological space. And then I said that, okay, so I have to just work with some of these Fs. And those Fs are, those pre-sheaves are what I call sheaves. And the idea was simply that everything is local here, right? All the maps are local. How to formalize locality? I said that, let's say that I have a cover of some U here, some object, and then these are something like this. So U is just a union of all U1, U2, U3. And how to formalize locality? Simply say that whenever I have some element here, say a function over here, or formally x1 is in fu1, and x2 in fu2, and x3 in fu3, if they are compatible on the intersections in some formal sense that we saw, then there exists a unique x in f of u, generalizing all of them. So you can glue local data to global, right? And then we call those f's sheaves. Not all f's are sheaves, some are sheaves. So I come back to the sheaf thing in a more general setting if you don't find it very intuitive. So, but the main point is that we can do it for C and then for the opens of a topological space. And then our goal was, let's go for any category C, right? And then to formalize this idea, we need some sort of formalization of union. And then for union, we add extra structure that was called the coverage. And the coverage was just a function assigning to any object, right? Some families of maps from something to A. A is always fixed. Some families that we call the covering families. Right? We specify some families and we call them covering families, but you cannot just pick any kind of family for any A. right? You have to have the following, the only property. And the only property is that whenever I have some A, whenever I have some covering family, one of these guys, right? A3, whatever, F1, F2. And any other map like this, for any situation like this, any covering of this guy and any map, let's say B less than A, there should be A covering over B, so one of these families in JB, such that each G, say G, let's say I, so focused on just G, GI, this composition must factor through one of the AIs. So some map here such that you have this guy commutate, right? That was something that we had. And we had so many examples of the coverings that I have to recall some of them because I need them. So if you remember, so the obvious one is just pick C as this guy. And then let's say that I have U and this, the maps are not important simply because, you don't have any. So you have this, say, if the union of UIs is U, right? This is just the usual union that we had. I said that you can work with a distributive lattice, right? Say bounded distributive lattice. And then you have some A element there, and then you have some things like A1 up to some AN, just finitely many. And you say that it is a covering simply when the join, which is finite, therefore it exists, is this. So it is just a finite version of that. Actually, I have to now add that one can generalize this to locals. So what's a local? Local is just the infinite version of this. So it's a lattice. It's a complete lattice, right? Complete simply because I want to have all the joins, not just finitely many, such that A, so I have this infinitary distributivity. Right, for any family. And so if you have this, then you have a local. Obvious example is just the open, simply because the union of everything exists, and then the intersection distributes over the union. And then again, you can just write the same thing, that you have A, some say AIs, not necessarily finite this time, and then it is covering simply when the join of AIs is A, right? And okay, so I can have more examples. I had actually more examples, right? So I had what? I had also this, that let's say that I have P and some, so it's a poset, or okay, it's a poset, say, and then A is covered by some AIs if the set of all AIs here is just exactly the set of all minimal elements below A. We had this guy. We showed that it is just a coverage. And we had this guy, the opposite of non-zero integers with just division. And then So you have n, some guys above. Since it is just opposite, then this means that it is n till some nk, and the coverage is just so the sum should be n. So in other words, since n is non-zero, just this multiplies, so should be just the coefficient m1 up to mk must be, the sum must be 1. And it is another coverage on any category. One coverage that I didn't mention is this one, I guess. So we had this category before, that's just some category, right? So then the coverage is this. So for any object, I have to say what are the covering families. For star, I say the covering is just the only map identity. And so actually the family, the only, and this guy is just the two maps. So if they are delta 0, delta 1, then it is one family of delta 0, delta, right? You can check that it's a coverage, so it's just obvious. And also we had for any category C, these are the general ones. So if you define J of A empty, it's a coverage. If you define J of A, say all isos to A, another coverage. You can define also this guy, say J of A as so I say that I have A, I have some maps. This family is a covering simply if for any map B, this map factors through one of these guys, right? So they are kind of, you know, the best. These are all examples that we had, right? So you can see that this is just a generalization of that, right? When you have also maps. Because, so simply what I'm saying is that when you don't have maps, then this is just a coverage in this sense. When anything less than A is less than one of these guys, right? So then you have all the minimums, technically. Okay, so it has a name. Maybe I have to also say it again. It's called dense coverage. And this is trivial coverage. Okay.
Is it just a explanation like this concept example, like if it is not minimal, then it might not factor through the minimals?
If it is not minim.
This B below A is for example, A, and A itself is not.
Yes, yeah, that's true. This is the topology constructed from that. That's true. They are equivalent in the sense that the sheaves for them are equal, right? But they are different. So if I have some B less than A, then there's no need that B factors, meaning that it should be. No. No, B can be anything, right? Less than A. And that B, here we are saying that it is less than one of the minimals. That's weird, right? Because if B is not minimal, then it's not less than any minimal. Huh? Okay, then what? Oh, then I said whatever I wanted to say. Okay, so let's go on and define sheaves. So I have now not just, okay, so first I have to say that if I have C and this more structure, then this guy is called the site. And so now I have the definition of, say, a sheaf. So a sheaf, say over the slide, this is, of course, a pre-sheaf, a function, such is a function such that for any object A, for any covering family, of course, according to J, right? Over A. And for any compatible, okay, let's say, what is the covering? So I need a name for the covering. So let's say that this covering, for any covering family, for any covering family like this, and for any compatible family that I define, xi inside f, okay, fai, whatever. There exists a unique x in f of a such that, so such that what? Such that if this guy is a, if these guys are f1, a1, etc. So ai, fi, and I have some x1, xi here, and it is compatible, and I will define what it means. But then there exists some x here, unique, such that f of f1, which is a map from f of a to f of a1, maps x to x1, and also for the others. So therefore, f of fi x is x I for any I in I. And what is compatible then? Compatible to this guy, each say in f of ai. This is compatible of course with respect to the covering family, if it is just if they are really compatible, as some maps on AI say. So what does it mean? It means that for any diagram like this, that you have a I, a j, for any a I and j, and something in both of them, say b, with some, this is fi, this is fj, some g, some h, such that it is commutative, right? So simply I'm saying that I'm finding via the map some b in both of them. Then of course I want xi here and xj to go to the same thing, right? So they are compatible really then. Then f of g backward, right, of xi must be f of h of xj, right? That's just too complex, but simply what I'm saying is this. So read any xi, since it is in f of ai via that interpretation, as some map over ai, right? I have some maps over ais, and then this is just covering a, all the a's. So you have some maps over these guys, and then this condition simply says that if you find something in both of them, of course, via the maps, you're respecting the maps, then the restriction of any two of the maps on the intersection, say B, is the same. Therefore, these are somehow compatible. Then I can just uniquely glue them together to get a map on A. And this unique is also very important. So you have to be able to glue them in a unique way. Unique simply means that the whole function behavior of this is just reduced to the local things. Okay, so is it clear? Not at all. So my task is just do some. Let's keep it. Do many examples to just see what's really happening. The first thing that I want to say, so each time I have to just specify one site, right? And then go for the sheaves there. So of course, the obvious site is the one we started with. So then let's say that we have just this. I don't say what is the coverage because it is just the canonical coverage, the union, right? So that is my site. And so let's play with this. What is the first example that I want to provide? So the first, okay, we had some before, right? So for instance, this guy, let's call it C. This guy, assigning to any U all continuous maps to some fixed space Y. So all continuous maps to Y with, of course, restriction. This is a sheaf, right? Why? Because if you open up the data here, so what do we have? It says that I have some U's covering this. So the union of these guys is U. Then it says that I have a continuous function here, 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 there, such that on the intersections, they are equal. So you can just glue the continuous functions to construct one unique function over the union, right? Simply, the reason, as we had before, is continuity is a local property. The same for differentiable whatever. And also we had this G last time as this constant. And we saw that this guy is not a sheaf. And formally now we know why, because to show that it's not a sheaf, I have to find a covering family, right? And the compatible elements over that, such that you cannot glue them or not in a unique way. Always you can do it in the unique way with this, that's important. Okay, I mean, if you can glue, it is unique, simply because it is just, it simply says that if you have a function on all the cover, then there is at most one function over the whole space. Of course, that's the case, because this is the only way to, there is only at most one way to glue functions together. But you cannot do it always, simply because if I have, say, my x is in a way that I have one u, one v disjoint from each other, then I can define a function in g of u. So my x, say 1, so my x, say, and y in g of v. So x, let's say f and g. So f is just a constant. So f constant 1, g over v is constant 0 and 1. Then, of course, I cannot glue them together to construct one function constant over u union v. The same for bounded. So if you have some, let's say y is r and then bounded means something, then if you have bounded, of course, it doesn't work, right? So because if you have just bounded functions on a cover, it does not mean that the whole thing is bounded. So these are the things that we had kind of before, but let's go for more. So is it clear what I'm saying or not? Really? Is it? Yes? Yes. That's good. So But let's work with more examples. So first, let me generalize this guy. Why not? Let's say that I have some map from Y. So as geometers like to do, so I have Y, I have this map to X, say P. It's just a continuous map, right? So continuous maps like this, if you fix your X and then you say that you are interested in Y and P, then people say that it's a bundle over X, right? That's just another name for it. There are different many versions of bundles, vector bundles, blah blah bundles, right? It depends on the case, but in this setting, just bundle is a continuous map. And the idea why it's called the bundle simply because if you have X here as some space, and then you can think of Y as the space over it, and you can think of P as some sort of projection. So if I have some X here, then there is something leaving over X, the fiber over X, and technically it is just P minus 1 of X, right? It's a subspace of Y. And then you can think of this as so many fibers assigned to any element glued together in some continuous way, right? So it is a continuous variable family of spaces, right? So you can just intuitively read this, the whole data, as say to any X. In the space X, I'm assigning some space, right? But this assignment of sets to elements is somehow continuous in some very vague sense, right? So this is what a bundle means. And therefore bundle is kind of a generalization of space, really, right? Because one specific case of this thing is that you use simply just always fixed Y, right? So nothing changes, it's just constant, Y. So in here it would be just, okay, Y is bad, so let's say Z. So simply I'm saying that your Y is Z times X, and this is really projection, right? So you can read this guy, if you read it like this, then it is just, right, a constant family of Z's. So this is, the bundle is some sort of generalization where you have different spaces for different X's, right? Something really varies. But anyway, formally we have just a map, a continuous map. But we think of it like this. There is none. So it is just something in pure topology, right? I have no category, nothing. So the only thing that I'm saying is that in topology, if you have a continuous map, you can read it as a sequence, continuous sequence of spaces, informally. That's it. Now I want to come back there and use the same C, but use also P to construct one, say, sheaf. And say the sheaf assigned to P, why not? On U, I define all this, technically they call it all sections of P on U. But formally, it means that I have, okay, so maybe here it's good first to explain. So what I mean by section, so U is something here, right? It's just a subset, open subset. And there are some fibers above it, right? Something here, right? So this is the part above this. So it's just P minus 1 of U. And what is a section? A section is just something like this. right? So then formally it is just a map, say R or S, why not S? S from U to Y. So S from U to Y, such that what? Such that if I apply my P to the element, it is over the one that I started with. So simply I'm saying that P composed with S is just identity over U, right? So in this language, maybe it is easier to understand, kind of. So a section simply is, so this is just a sequence of spaces indexed by X. So a section is just, say, S of X, such that each S of X is in the fiber and X is in U, so local, right? What is then F P of U subset of V? Because it should be a functor, it is just restriction. And that's just trivial, right? So if I have a section and if I restrict it, then it is also a section, right? Just pick a sections. Yes, of course, yes, always. Yeah, always here, everything is continuous. And then this guy is also sheaf. This time the reason is what? So I have some elements in F of UIs, right? To check it's a sheaf. And UIs cover U, everything is compatible, I have to be able to glue them, right? So what does it mean? It means that I have some U's covering this U. On each of them, I have a section, all of them compatible with each other. So you can just take the union, right? So this F of P is a generalization of this F, right? So you can read it like this, that here I'm saying that point all F, so, okay, continuous functions such that for any X in U, I pick an element in Y, constant Y. But what if this Y also depends on the X? So then here I don't just pick some element. So here it is, okay, write it like this, that it is just continuously X in Y for any in U, right? So what I'm saying is that maybe Y of X also. So the fibers also depends on X. Right? Okay, whatever. So I have just for any bundle, I have some sheaf assigned to it.
But this sheet, that's some kind of subsheet of that one, was like every section is part of the function. So like of your setup more than that before. So
Yes. Yes. Yes.
the extent say it is called.
Exactly. So so it means that then in the category of sheaves, this guy is some object of that. Let's say. Okay, so let's now play with something easier, maybe. Yes. For any U sections on U. Then let's just do some sort of crazy exercise. So first, what happens to the constant functor? So maybe that's a good thing, right? So let's say that I have a fixed set A, and I define my functor, say this time f of A, on any U as just A, and on anything, any map as identity, so it's just a constant A everywhere, right? Is this guy a sheaf? It's just one set A everywhere. Nothing changes. Never. Is it a sheaf? Do I need this? Yeah. When everything is a function, we have some sort of intuition, right? That it is locally, we can glue them, right? But this is just too abstract. It is just look. And it's a very well-behaved functor. It is just a constant functor. So we expect that maybe it's a sheaf, right? So why not? And let's see. Okay, if it's a sheaf, then I have to have the following property, right? So let's check it. I have some U and a cover of U, let's say U1, U2, why not, right? Just two. And so first, the sheaf condition says that if I have a compatible elements in these two, let's say that X in F of U1, X1, X2 is in F of U2, and by the way, both of these guys are A, right? Then if they are compatible, I can just, glue them together. So what does it mean to have a compatible family? So this is simply just a pair, picking a pair in A times A, right? So is it compatible when what? When for anything here, I have, right? So since everything is just, you have just at most one map, let's work with this U1, U2 here. Then simply it says that if I restrict X1 like this and restrict X2 like that, right? Then they should be the same thing. But the restrictions, the maps, the functor over these guys are identity. So simply I'm saying that X1 is X2, right? Is it true? So then I am saying, okay, yes, but okay, X1 must be X2, right? So if I have XX, then always this guy is just compatible. And you can construct this from unique X here, right? Therefore, it's a sheaf. But it is not. It's not sheaf necessarily. So what I'm missing? Hmm? A should be non-empty. Fine. Did I use it really? No. Because you start with two X's, right? You have a covering family. You have two X's in A. And then you see that they should be equal. Okay, whatever. And then you find one X here. So since you started with one X, you have one X here. The uniqueness. So because the maps here are identities, right? So then whatever I have here, let's say Y, then the elements here and there should be Y. Therefore, I have just X as the only choice, right? So I don't have anything else. The reason is just extremely stupid. So there is one covering. Okay, so this is just covering with two elements, right? Of course, covering with one is just stupid, right? Because it should be the same. And with any infinite or whatever finite, you do just the same thing, right? You pick just two, and then everything is equal. So the problem is with empty family. It is possible to cover empty family. Okay, let's say like this. So I have empty set, and I can cover empty set with empty family. What is empty family? So any family is something like this, right? So let's say that I is empty. So there is nothing, right? No, nothing. And empty is covered by empty. Simply because if you have empty family, the union of empty family is empty, right? And therefore the union is this guy. So nothing covers empty, which is very weird, right? But it's the case. So if it is the case, then what is the covering family? Sorry, that's the covering family. What is the compatible family of elements? Of course, I cannot pick anything because there is nothing, right? So whatever you choose is a covering family. But for any covering family, you have to have a unique element in f of this guy, right? So I'm simply saying that whatever you do, f of empty is always unique element. So it's a singlet, say. Right? Over empty. So we have the same thing actually here, but it is just ridiculous and we cannot see it. For instance, here, f of empty to y, there is just one function, right? Over empty. So what I'm saying is that just forget about this a constant, whatever. Whenever I have a functor, which is a sheaf, f of empty always is a singlet because the argument goes for any, right? Right. So first, if I want to find just examples of non-sheaves, work with functors such that f of empty is nothing or not singleton or whatever, right? And specifically this bad guy, right? Because this says that f of everything is a, including empty, and that's bad. Except a is a singleton, right? If a is a singleton, then maybe it's a sheaf. But if a is not a singleton, then f of empty is not a singleton, therefore it's not a sheaf. So if a is non-empty, not a singleton, if a is not a singleton, then f of a is not. The constant actually never is a sheaf, except for one case, is not a sheaf. That's kind of weird, but that's the case. And you can see that we checked everything except one weird case.
What level of generality are we now? Are we still like taking open sets?
Yes. Just over the open sets. So then what if A is a singleton? Then, okay, A is just a singleton, star. And now f of my A is of any U is just a singleton. Always everything is identity. And of course I can cover this case. The rest is just in case. So, but if you don't care about these things, it is just obvious, right? You have just one element everywhere. Of course, that one element is compatible with itself, and then you can glue it to one element. So that's just obvious, right? So this guy is a sheaf. Right? That's a very weird one. Then what? Then let's check this guy. What are sheaves? Okay, what's up? Why not this? So again, the same C, but now this time F goes. So let's call that singleton constant singleton constant. Yes, this is a sheaf, right? So my problem is this question: what are which subfunctor, which sub object or sub, let's say subfunctors, but subfunctors of this guy is a sheaf. What is my object? My object is just constant singleton everywhere.
Is this still in this topological case?
Yes. Yeah. For now, just the topological. C is just the opens of C. Huh? Yes, triangle is delta. And simply it means delta is just a constant functor, right? So when I write delta A, and in this case it goes C opposite to set, right? It means just everywhere A identity for any map, right? So that guy is a sheaf, we saw that. So now there are some subfunctors, meaning that some subsets of the set star assigning for any U, and which of these guys is a sheaf really? Let's say F. So when I say that F is a subfunctor of this, simply I'm saying that F of U is either empty or a singleton, such that if U is a subset of V, then F of V is a subset of F of U, right? So if you make something star, then everything below is also star. It's a downset, right? So which of these downsets is a sheaf? So what is the sheaf condition? We should check it. Right? It's a bit hard to imagine, maybe. But what does it say? Again, it says that this is union of UIs. I have some U1, U2, etc., right, as a cover. And then what? It says that if you have some element here, there, if it is compatible and you have just one element at most, so then you can just glue them and find one element at most here, right? So what do I say then? I'm simply saying that if for any I, f of ui is non-empty or it is a star, then f of the union is also star, right? So if any f is a downset, I'm saying that f is also closed under union, right? So if let's say that you have a downset of this guy. Any downset is just what? A pre-sheaf. A pre-sheaf, but actually a sub-pre-sheaf sub-object of delta star, right? And then downsets closed on their union, right? Then they are sheaves. And then what is a downset closed on the union? Because that's just a ridiculous thing. It's just a principal idea, right? Because you can just union everything in the guy, and then there's top element then, and everything else is just less than this, right? So any downset is just actually nothing but downset of some U. Pick just U as the union of all the elements. There, all of them exist, therefore the union exists. And since it's a downset, everything less than that U exists, right? In the set. So any downset closed under arbitrary union is just downset of some U. And this guy is just the Yoneda. This is a downset, of course, but corresponding to this Yoneda, the Yoneda of U. So what I'm saying is that all the Yonedas are sheaves, and just for the subobjects of this guy, just the Yonedas are sheaves. Right? So if you want to know that, later we see that this guy is actually the one object, the terminal object in the category of sheaves. And then what I'm saying is that sub 1 is actually isomorphic to O of X. Right? So you can recover the topological space underlying the whole game as subobjects of the terminal element of the sheaf category. I'll come back to that later. But something else. Let's say that I have let's say that I have so let's say, okay, so let's be kind of ambitious even. Let's say that, is it possible to somehow characterize all sheaves? Right? Why not? Because some of the things that we solved are some sort of characterizations in some cases, right? At least all constants, all, right? Between all the constants, we know one is a sheaf. Between all the subobjects of the constant, we know what are the sheaves, right? So maybe we can say something about all the sheaves, huh? So, but that's just hard. So let's just cheat. What if X is discrete? And therefore, opens are just the whole power set. Yeah, yes. X is fixed, all the opens. I want to understand all the sheaves. But for now, let's assume that X is discrete. Therefore, this guy is just a power set of X. And then what are all the sheaves here? What are all the sheaves? Just tell me. Any idea? What are all the sheaves? All the functors? No. This is not the trivial topology. This is not the trivial topology that we had before. It is trivial topology, but it's not the trivial coverage. So there are something to check really. So the sheaf condition matters. What do I say really, huh? So the sheaf condition says what? It says that if you have some U as union of UIs, right? Then kind of the whole f of U is determined by f of these guys, right? Of course, it's not just any elements, but the elements such that blah, blah, right? That you have compatibility. Now, if I write U here, and if I put here all the singleton X, such that all the X's are in U, right? That's a cover, that's just the worst possible cover. And I can do it because it's discrete. And then any element here in f of U, any element in f of U, something in f of U, is actually a sequence of compatible things. There is one-to-one correspondence, right? And what is a sequence of compatible things? Every sequence is a compatible. Because these are different x's, there is nothing you know, in the intersection. So whatever I choose over any x in f of x's, then that's it, right? So the product of the whole thing is just f of u. So what I'm saying is this, that actually f of u is nothing but the product of f, okay, some sort of equivalent with this, right? If it's a sheaf, right? And this is just a set. Right? So essentially, I'm saying that say what is f of any singleton x, and there is no compatibility condition because nothing of these guys is inside the other, and then define any f of u like this, and then you have your sheaf, right? So therefore, sheaves are kind of over, of course, discrete. X is nothing but a sequence of sets assigned to the elements inside X, right? So something like this set. These are sets assigned, right? Some family of sets, whatever. Who cares? Huh? Right? Right? So, and this, no.
No, that's good, but maybe you could just say what happens to this example if you don't have a sheaf. Let's say,
If I don't have a sheaf condition, then I don't have this thing. Therefore, I can just define f of u whatever I like, as long as f of v is less than f of u in some sort with some map. And you know, you cannot decompose them. So for instance, let's say that as we had before, f of u is just a constant set A always. Right? That's a puncture, that's a pre-sheaf. Right? So everywhere I have a set fixed A, but that's bad. Right?
I guess I was expecting there would be more. Functions.
Yes, there are more functors, yes. And this is one of them. The constant functor, for instance, is one of them, but it's not a sheaf. You know, the point is that when you have just a pre-sheaf, to parts, not elements, to parts, the open parts of, say, the space, you assign sets in some sort of compatible way. But the only thing you have is just some sort of anti-monotonity and nothing else. But this makes it possible to kind of, you know, break it to some opens, some small opens, and in this case, just two elements because it's discrete. But anyway, you know this guy, right? Yeah, I told you. If you want to have, let's forget about topology. If you want to have a family of sets, yes, fibers over some space, you work with what? You work with one map to from some space to X, right? So any P minus of any X is A of X. So in this case, this is just the discrete space. And P is projection. And the fiber of any X is A of X. Huh? Okay. So any sheaf then is F of a bundle. Huh? Of course, that's just a fancy way to say that. That's better. It's more concrete. But I want to have a way to generalize it from discrete to anything. Right? So what I want to say is this. This is now my conjecture. That let's say that I have any functor, any sheaf. So any, let's write it like this, any sheaf f over x, meaning, you know what, is actually f of some p for some bundle p. Can construct always all the sheaves with bundles, right? So if we change this situation such that A of x is a space, not a set, and it is continuous somehow with respect to the change in x, formally it's just a bundle, then any sheaf can be described like this.
Right, you're generalizing your. Screen.
Yes, to any space x. To any space x. So this is just the same, but x is not discrete anymore. So I have to prove it, but I won't, of course, right? That's just too much. But the idea is that you have to ask yourself, what are these A of x's? Simply because I cannot just do the same. I cannot, kill you as a cover with some elements. But at the same time, you can just go for the neighborhoods of x, smaller and smaller and smaller, smaller, and then this is some sort of limit there, right? Therefore, that thing is just some functions over small amount around x. So that is technically called germs of f around x. But anyway, what I'm saying is that we can just do the same similar thing with more care to prove this conjecture to actually a theorem. It is possible to construct all shapes in this way, right? So when I say sheaf, you can just simply pretend, that's just category, functor, I don't know. It's just a bundle. Let's say that the guy said that I have a bundle, right? And then work with bundles, sure. Yes, exactly. One continuous map and nothing else. A bundle over x is a continuous map to x. That's it. What's the bad thing about this characterization? The good thing is that this is far more primitive, right? It's just a continuous map rather than this huge machine of sheaf or whatever, right? That's good. The bad thing is that the correspondence is not one-to-one. There are different bundles going to one sheaf. Therefore, I cannot pretend that the category of bundles over X, like maps and triangles, is equivalent, say, to the same as the category of sheaves. That's not true. But it is possible just to pick some as the good ones, right? As the representatives, right? And then work with some bundles. And then the categories would be the same. And some bundles are called local homomorphisms or étale maps. And it's just not that complex thing, right? So it simply says that you have this, and it is local homomorphism, meaning that for any element here, there exists some neighborhood such that this thing is, so P restricted to this U, to its image, is just homomorphism. Locally, it's homomorphism. That's just enough. So if you restrict yourself to these guys, you get all the sheaves. So it's just some stronger version of this, right? Not a bundle, actually an étale map does the work. And if you restrict yourself to the étale maps and work with this category of étales over X, meaning the objects are these guys, and then the morphisms are something like this, right? As we had before. So over category, then this is actually nothing different than the category of Sheaves over X, right? So I can just pretend that I'm working with bundles, but if I want to work really categorically, then I'm just working with étale maps, local homomorphisms. Okay, so that's good, but FP is the construction that I had before, right? That section thing. Yes, section of the P. Of something. Of a bundle, exactly. Okay, so that's good, right? Now I have actually the equivalence between categories. So from now on, I can just say, okay, whatever, sheaf is just too complex, right? Let's work with étale maps. Exact, that's the problem, one of the problems. One of the problems is that I have it for that specific case of topological space. My C is a topological space. My cover is exactly that union cover. And yes, for that case, I have this easy thing. And for obvious reasons, this is just historically the first kind of. Of course, we didn't have any kind of sheaves, categories, whatever, but people work with this. So for instance, Riemann worked with this. When you want to have continuous functions with multi values, say. So what do I mean by that? So first, remember this, right? You can read this as what? As the whole thing, the whole family, right? It is some sort of function to any x, it assigns a set, not just one element, right? It's a multi-valued function. If it's a bundle, then it is a continuous multi-valued function. And in practice, it is important to have some sort of continuous things in that source. So for instance, we all know the famous Riemann streak of using surfaces. So for instance, here is the example. So let's say that I have this S1 thing, right? It is just a circle. And then is it possible to read any element here? And then let's say come up with some angle function that goes from S1 to R and then reads any element and find this angle in a continuous way, right? It's just a log function in C. That's a very reasonable thing. And of course, in some sense, it is continuous, right? Because it is continuous. But it is not, because when you go here and then when you reach here, then you have to go from Z to from 0 to 2p, which to maintain the continuity, right? If you go for 0 again, you kill the continuity. If you go for 2p, you kill the value because you are saying that it is single valued, right? So what is the angle here? Either it is 0 or 2p. Riemann streak was okay, no. It is all multiplies of 2p's, but this is not a function, right? It's a multi-valued function. And we understand just functions. So then let's work with this bundle. And bundle is what? It is R to S1 and map any theta to say EI theta, right? And then any section here is some sort of thing. And then if you think about it, we all know that, right? It is that thing, right? So that's the trick of having different layers, multi-value things as layers, right? As bundles. That's an elegant approach, except that you cannot use it when you work with something more complex than topological spaces. For any topological space, I can do this trick, right? If I have a multi-valued, say, function, continuous, but somehow not over the opens of the topological space, but on some category, then I cannot kill it by this trick, right? And it really happens. So where that's just too complex to explain. But let's say we have similar situation exactly like this, but in algebraic geometry or say in algebra. And then these are some algebras, so technically some fields, say. And then you can see that in some sense there are some opens U such that restricted to that U, everything is just one value, everything is good, right? Like here. So if you go for some small U, right, then you see that you have the angle. So you can do the same thing, but the problem is that this U is not subset of your space. There is some map to your space, some general map. So you have to change your notion of open from subset to some maps to your space, right? And therefore you are forced to go from opens as subsets, as we have there, to a category, right? And then you have to work with multi-valued things over some category, and this trick does not work. So you have to work with some sort of coverage and sheaf and etc. Right? So that's somehow the real motivation that Grothendieck came up with the idea of using sheaves. Okay, so what else? Maybe that's enough for just that site. For other sites, let's do something.
Can you please explain one more about that is?
Yes, of course. It is local homomorphism, meaning that for any element here, right, there is some small neighborhood such that the restriction of P to that neighborhood is just a homomorphism from that U to P of U. So locally, it is homomorphism. Homeomorphism. Because it's just topological map, right? So it's one-to-one. There is a converse. The converse is also the continuous. Yeah, of course, this way. So any element, there is some U around it, such that here and there is one-to-one corresponds with theta and the, but of course, yeah, the whole idea is that you open up kind of the the winding thing. So yes, another site. So another site, okay, this is the dumb site that we had. Let's say that I have this as my C, and you know what the site is, as I said before, right? So these two cover this guy, and just identity covers it, and then what's a sheaf? Because any pre-sheaf we know is a graph, right? So any pre-sheaf is just two sets, two functions that we can interpret as source and target, right? We have a graph. Pre-sheaf is a graph. What's a sheaf? It should be some sort of graph, right? Graph with some condition. Let's check it. So what does it say? It says that for any covering family, like this, yeah, right? That's one covering family. For any compatible elements in F of these two, meaning that for any V and U in V, for any, right, two vertices, such that it is compatible. And compatible means what? Means that if you can complete this diagram, blah, blah. But you can never complete this diagram, right? You have just identity here, and these two are different, right? So therefore, any pair, actually, is a compatible family, right? any pair of vertices. So then the sheaf condition says that any pair of vertices comes from exactly one edge. Right? So what I'm saying simply is that the graph is complete between any two elements. There is one edge and there is exactly one edge. Which is just stupid, right? So this is just very restrictive thing. There is even force, I will say, in a moment. But let's work with another one. So you remember that I had that P thing and then with the minimal coverage, right? So let's say that my P is this guy. But read it backward. Right? So this is less than this. So, and the coverage is that coverage that we had. So if you want to cover this, then all these elements. If you want to cover this, all these two elements, right? So all the minimums. So above is less. And then let's put some name, P, atom P, PQ, P negation Q, negation P, negate, okay, Q, and negation P negation. It's kind of decision tree, right? So, okay. So then think about this guy. Two functors. First, F. To any node, I have to assign something such that when I go up, I increase, right? So then for any node like this, like this, so let's say that for this node, for f of p, let's call it this p and this empty and etc. So f of p is just, so fix a formula. What, 5? And then it's star if p proves phi classically. And otherwise, it's just empty, right? So this F, what does it do? It encodes the probability of phi, right? With that amount of information. So if you can prove phi with P, then you put star here. Otherwise, 1 or 0, right? Otherwise, 0. If you can prove it here, then you can prove it there and there. Of course, it maintains, right? And so that's it, right? So you capture based on partial information, can you prove phi or not? And define your G the same exactly, but this is intuitionistic proof phi, right? Restricted just to the intuitionistic. Both of them are functors, but this guy is a sheaf because it has a sheaf condition, right? What's the sheaf condition? The sheaf condition here simply says that if you have a cover, say I have this guy and this is my cover, if I have a compatible element here and there, a family, and since nothing is there, right? Every family is a compatible family. So, but it doesn't matter, right? Simply I'm saying that I have star, star. So star, star simply means that this proves phi, this proves phi, therefore this also proves phi. Because of the negations, right? So therefore it's a sheaf. But this is not a sheaf with that coverage, because if P and negation Q and P and Q prove something, P does not prove it necessarily intuitionistic. You see that I am capturing classicality, one of the problems that we had, using this sheaf condition, right? Another example. Sure. The other way around. Both of them are pre-sheaves, but this is a sheaf. Classic one is sheaf. So here I can say, I can dare to say, but later we will see it really that's true, that Sheaf means being local, right? Classicality is some sort of being a sheaf. Therefore, classicality is some sort of locality. Everything is intuitionistic, but for some notion of locality, some coverage, you get classicality. So classicality is some sort of locality. There is some interesting thing happening here, right? But then what else? Then what else? So this example, maybe I have to let's complete all the examples that I have. The next example that we have is for that cover. What was that? Z cover, right? So you remember that we had this cover over that, right? And then I won't prove it, but I just say I have some equations. Say I have this equation, I don't know, or whatever, some equations in, say, k variables, right? And then define f of element of n as solutions or roots of this set E of equations in this ring. So this simply means that you can invert n. So it is A over n some r for any r. Right? This ring. Okay. So you see what I mean, right? So if, for instance, in f of 2, I have a root for this guy, right? It's 1 over 2. But in f of 1, I don't have it because f of 1 is just z. So I'm recording in different z of 1. So some rings in this form, not all the rings, I'm recording all the data. And then if n divides m, then you can see that actually f of n is less than f of m, simply because if you can, invert m, then you can invert also n. So any element here is also there. So it's a functor. Actually, it's a sheaf with that property. So this is my baby version of something that's called a Zariski coverage. So Zariski coverage is, let's say, that commutative rings, all commutative rings, and there is some coverage there that's called Zariski coverage. And the definition is that you go from R to R1 over R1 up to 1 over Rn. And this is a coverage. Of course, it should be opposite. So then, therefore, in this way, if and only if the sigma of Ri is 1. So this is just a baby version of this. And the point is that these equations, and then if you define f of any R as roots on R of some E. So if you remember, we had this guy as some sort of functor, and this functor is actually the modern version of roots of equations, right? Because when you ask roots of equations, so you ask where. So let's say that parameterized with R, it can be anywhere. And let's work with this f as a functor to understand the roots, right? Roots everywhere, parameterized. The point is that it's not just a presheaf, it's a sheaf. So you don't work with all the presheaves, with sheaves and even more, but that doesn't matter for now. But that's just too complex. A good exercise is just to show that this guy with this thing is actually sheaf. So I constructed that to avoid ring theory. Then what? And maybe I have to say something about the general cases at last. So if you remember, we had some generic coverages, right? So if you have a category C, one coverage, the trivial coverage was this empty, right? Huh? So what are the sheaves? Every pre-sheaf is a sheaf because there's no condition, right? Being a sheaf means that pick a covering family and some elements such that blah, 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 but there's nothing. So therefore, every pre-sheaf is a sheaf, right? So yes, sheaf is some sort of restricted version of pre-sheaf, but at the same time, it's a generalized notion because pre-sheaf is also sheaf for different coverages, right? But then if I prove something for all the category of sheaves, I also cover this set to the C opposite as one of the cases, right? So I'm really generalizing, not really restricting. So what happens if I have this? I forgot to mention this. So one of the coverages is that every family. Let's say that any family that we can think of maps going to A is just the covering family. That just, like topology, you have two obvious topologies, right? The trivial and the co-trivial one, and these are the two. So what are the sheaves for this? It should be extremely restricted, right? Because here I have nothing, and here I have everything. That's hard to think of, except that if you remember that game with empty that I had. So let's say that I have some A and use just the empty family. Because any family is a covering family. And then write the exact argument that I had for the sheaves to understand that f of A should be a singleton, right? Therefore, if f is a sheaf, f of any A is a singleton. There is just one sheaf here, and it is this. Yes, so you remember that argument that we had for the empty and the empty family, right? Yes, we said that f of empty is just singleton. And the reason, yes, because the empty family is just a covering family. Let's explain it here, right? So for anything is a covering family, including an empty family, and then it means that for any compatible element here in this family, which is just nothing, there's none. Actually, there's one because there's just one obvious function. There should be exactly one element here such that blah blah, right? The glued one, which means f of A is a singleton. So there's just one. So later I explained that if I have C and J aside, all the sheaves, this is a category which is actually topos, right? And it's called the Grothendieck topos, of course, because Grothendieck constructed. And then, and this shows that pre-sheaves is one example here, right? I'm actually generalizing one example that I had before of toposes to something more. But here I can see that one is the category with one element is also a sheaf. Actually, we saw it before, right? It is set to C opposite, let's say set to 0, it is 1. So this is just one of the obvious sheaves. It is just inconsistent setting, right? That everything happens, everything collapses, whatever. And just let me to say the last thing, and I'm sorry to go over time because just let's just finish it. The last thing that I want to say is this, that if I have, let's say that I have some C, J, some site, and then I have A and some covering family, A1 up to AI blah blah, and this F1 is ISO. So I have a covering family and one of the edges is ISO. So then there's nothing to check. The shift condition just disappears, right? There's no condition. And the reason is simply this, that what is the shift condition? It says that if I have some compatible family, then there should be unique X, right? So what is a compatible family? Let's say that I have a compatible family, and then, of course, intuitively, when something is isomorphism, you have this guy already here, right, in your coverage. So then you have the whole, in X1, the whole data is there. But formally, it means that, that what? That if you can find something here that you have, the commutativity, then Xi's are compatible, and then I have to pick this simply. So A and AI, and here I use AI and identity and Fi and F1, and so this is Fi. It should be F1 Fi F1 minus, right? Since it is ISO, I can put it there. So this is just commutative, meaning that this X1 and Xi must go to the same thing here. And this is identity, so it is Xi. And this is F of F1 minus Fi of X1. And F is changing the orders, meaning that this is F of Fi, F of F1 minus 1 of X1 is Xi. So I can construct all the Xi's by F of Fi of something. And this is my X that I want to find. And of course, it is unique because if I have two other things, then this is ISO, then I can show that they are equal, right? So you see that when I have a compatible family, already I have my X. So there is no condition to check. So whenever you want to check some shift condition, so you can just forget all the covering families that has one at least isomorphism. More than that is true, but just let's forget about it. Then it means, for instance, that if you work with this that we had before, right? J of A is all isos to A. That one was a coverage that we had, right? So what is a shift then here? Everything. Because I'm saying that if you have a covering family and one ISO in it, just forget about the covering family. There's nothing there to check. So you forget about the whole covering families and everything then is sheaf. So this is kind of no different from the empty, right? Sheaves are the same. And I guess that's just enough. Next time, I want to show that this guy is a topos. And then I also want to see that what is the relation between C and this guy, like the pre-shift that we had. And remember that I didn't solve the problems that I mentioned, right? I said that there are three problems. The geometric one I solved. This is the geometric one, right? Just work with the local things. Now I want to say that if you have this setting, you can solve the other two. We had the glimpse for the solution for the classicality using some sort of coverage. But the algebraic thing, we even don't know what it is. So I have to explain it and then solve it. Thanks. Any questions if you dare to ask? Yeah, you're keen to find the end. I don't know really. So we are just so slow. Yeah, they don't believe that it is too slow. I guess maybe, okay, we have to think about it, but maybe we can just cover the whole topos theory thing, and then later in another semester come back to cover the logic and the independence. Right.
Focus on the logic part, skip some of the topics.
I can.
You need some motivation. That was the only way about purpose in this semester we used motivation.
True.
It must give us a reward.
You have to be patient. So it is just deadly hard to start with nothing like category theory and cover topos theory this much through Sheaves, say in 10, 11 sessions. Just that's just hard. So but if you want some motivation, can I do some sort of cheating? Yes, I can. Okay, let me think about that. One way to do it is just to cover this Grothendieck process at least for 1-2 sessions, and then just focus on the interpretation of logic in these guys instead of toposes, and I forget about other constructions of toposes. And then later maybe we can come back for other constructions of toposes. Is it good or bad?
Yes, well, maybe you could start next time by just some outline of, maybe we'll understand the general idea better. I mean, of how you would get to these interpretations.
That's also possible. No. Okay, first, knowledge is good. Not necessarily applications, but the point is that so far we have enough things to prove realism independence. Because we have one construction of toposes. At least you have to have some construction of toposes, and we have one. And pre-sheaves are not enough, as I said before. We need sheaves. But of course, you cannot prove other things because you need other constructions of toposes. But at the same time, maybe you don't care. Okay, so let me just do some voting, right? Based on the presence here. Do you want to see more topos theory by showing of hands?
Actually, can you put the question?
That's already no. Yes. Do you want to see? Okay, these are the options. Maybe that's the favorite version. Do you want to see more topos theory and then the connection with logic and independence, or first with some connection with this is the second, the connection with the independence, and probably just that one semester and no topos theory at all ever again. So for one. Even you are then that's just okay. Just you. What about you? Yeah, 2. Most good. So you are for 1 or what? Or 2? For 1. For 1. Okay. I'm sorry. You lost it. But okay. But I can.
Like 20 minutes overview, like next time.
Yes, but I can do something good, really. So one of the things that I can do is just I can change the structure like that. When I complete the sheaf thing, I come back to say that, okay, we don't know how to interpret logics in any topos, but I can tell you in one session how to interpret logic in these toposes. And then that could be useful. No. What do you want, really?
Like one session.
Yes.
Which was also
In this
Yeah.
sheaf.
And then go.
Yes, that seems like the best option for me as well.
Okay,
Well, I don't understand how the relation between the thing you said now and the general goal of the series should be independent.
uh-huh.
So I feel like I would need to see the lecture outlining.
But just the outline is enough.
Before-
I guess it is not.
Before I could provide it with any question on this.
Okay, even I can say now. So the outline is this. I want to construct all the toposes that I can. Three ways to do them. This is one of them. There are two others, but not that intense because you can't just explain things easily. So that is the hardest one. And then I have some constructions of toposes. The second thing is that what is the connection between logic and topos, right? How to interpret logic in any topos, including these guys. And when you see that, then you can interpret logic specifically in these three versions. But of course, now you have to have some concrete way of computation things because it's just too abstract. And now you can prove all the independences that you want.
So forgive me, but why do you need three versions?
Because I want to prove different independence results. And you cannot prove all of them with one of them.
But you could do one, then everybody gets excited.
Okay. Okay, fair enough. Fair enough. You all prefer this, right? Let's
Yes, we all.
end of discussion. Yes. But you also prefer, right? So let's just cover this Grothendieck thing, then do some independence really with this thing, and then we go for other constructions, and probably at some point for the whole interpretation of logic in toposes, or even maybe not. So
We'll see.
yes.